Professor Fernando Fraternali. He's one of the most well-known mechanicians in Italy, for sure. He's an expert on metamaterial composite structures. I've seen his name associated with the composite part B in long
in the
time.
past with
And he has been collaborating with the United States. In particular, I know of his collaboration he has been visiting Caltech, one of the most prestigious North American universities. He received major international awards. One that comes to my mind is from the Society of Experimental Mechanics. And today is going to talk us about dynamics, so I'm particularly interested in that, and this is your time. Thank you.
Thank you, thank you. So thank you very much, Professor Amabili, for this kind invitation to this exciting conference on the nonlinear solid mechanics. I will deliver a lecture. I hope it will work fine, the microphone. I need to stay on this side of the desk because I need to run some animations. And so I need to, these are external animations, so I need to run external movies. Hopefully you will hear everything. So this talk is on the nonlinear wave dynamics of tensegrity metamaterials. I have been visiting the United States, as Marco told you, over the last 20 years, several times. And during one of these trips, I met Bob Skelton, who was one of the pillars of tensegrity system, tensegrity structures. So he involved me, he taught me many tricks about tensegrities that we have applied during the years to combining the tensegrity concept with the concept of metamaterials. So, let me go to the outline of my presentation. I will present the concept of tensegrity metamaterials, the main goals of the ongoing research. Then I will present the two main topics of the talk, which will be the bandgap response of tensegrity metamaterials, some particular examples of tensegrity metamaterials, and the second topic is the propagation of solitary waves, which is another metamaterial type behavior of tensegrity structures. In this case, for this second topic, which is more focused on the topic of the conference, since it profits from the nonlinear nature of the response of tensegrity systems, I will first present some analytic results for 1D systems and then some numerical results for 2D and 3D systems. I will end with a discussion and outlook. So, the nonlinear metamaterials are artificially designed and fabricated materials that can tune their response to the level of the applied stress and the amplitude of the traveling waves. In this wide category, we are interested in particular, my group and I are interested to tensegrity metamaterials. These metamaterials have a peculiarity due to the fact that one can tune the response of the system, also playing with internal and external pre-stress, in addition to the topology optimization, the size optimization of the members. So this pre-stress feature of tensegrity is peculiar and permits to control the speed of sound and to control all the effects that we will analyze during the talk. What are the lines of research which are active in this area? One, I summarize some of the main areas of research in the area of tensegrity metamaterials, meta-tensegrity, and one line is concerned with the tuning of the mechanical response, acting on pre-stress mainly, and with this tuning you can basically design any nonlinear response you want. For example, you can design a power law response with an exponent of any particular value. Another line of research is about the use of tensegrity metamaterials as impact protection devices due to the solitary wave dynamics, in particular one type of solitary wave dynamics of these systems, and the rarefaction wave, solitary wave dynamics. Another research is profits from the compression solitary wave dynamics of a different kind of tensegrity metamaterials. The compression type solitary wave dynamics can be employed to design devices that can focus mechanical waves in narrow regions of space to design, for example, tensegrity acoustic lenses. And finally, the most straightforward application is that of I turn it on. It's on.
No, it's on.
Yeah. Okay. Okay, now it should be better. Thank you. It's not, but it goes on and off. It goes on and off. Now, probably the battery is... yeah. Okay. I will speak loud. So the bandgap response is the basic type of metamaterial response, and we will see that we can control the bandgap regions of tensegrity metamaterials in different ways. So, starting with the bandgap response, in this slide I'm anticipating one of the systems that we will analyze. This is a recurrent system formed by tensegrity prisms and lumped masses, disks, heavy disks that are interposed between tensegrity units. We use the tensegrity units as a nonlinear springs, and in particular in the bandgap response we can linearize the response. This is an illustration of the bandgap response. And we can tune this response to the pre-stress of the system. And another interesting feature is that of tensegrity metamaterials is related to the solitary wave dynamics. So I'm anticipating a behavior that I will describe later in the talk, which is that of a mass spring chain with a softening type, elastic softening type response. And such a system, as we will see later, is able to exhibit peculiar metamaterial response because under compressive disturbance at one end, applied at one end, maybe an impact disturbance, it will develop a rarefaction, leading rarefaction pulse traveling to, this is a chain of units, tensegrity units separated by lumped masses. So there is an oscillatory tail that follows the leading rarefaction pulse, but as long as during the propagation of the wave through the chain, the amplitude of the rarefaction wave will progressively shrink. So in the end, if the chain is sufficiently long, only the rarefaction pulse will propagate. So this means that by pre-compressing a tensegrity mass spring chain, we transform a compressive disturbance into a rarefaction of waves, so we release part of the initial pre-compression of the system. So basically, this impact is not transferred to the other end of the chain. So through the years, we have also experimented the manufacturing of tensegrity structures in different ways. Obviously, we have experimented. So we have also another very bright researcher, Professor Paulino, who has worked in the tensegrity research field for many years. Now he will deliver a following talk on origami, but he has worked in this area for many years. There are many techniques have been experimented to manufacture the tensegrity systems. I'm showing you some samples that I will ask my collaborators to circulate. Some samples that we have manufactured are made of titanium alloy, and they were 3D printed through electron beam melting. And but this was only for the compressive parts, so for the bases and the struts from the system. And in addition, we added at the end, there were some sacrificial supports that then we removed, and we sewed the structure, the 3D printed structure, with some cables. We did a post-tensioning approach, because one of the main problems with tensegrity is to 3D print the cables. So it's not very easy to 3D print the cables. And this is one technique that we have employed. Another technique at the micro scale, there is one sample. This sample is at the millimeter scale. So this is exactly the red sample, which is 2 millimeter tall. This has been fabricated through another 3D printing technique, which is the micro stereolithography. In this case, we use an optical procedure to manufacture the sample, and we used some swelling materials for the cables, for the tensile members. So once dried, these tensile members contract, and so a pre-stress state is induced into the system. So I'm still in at the introduction, and I want to summarize the source of nonlinearity, which are the sources of nonlinearity of a tensegrity system. Let's start with the standard tensegrity prism. You will also see one sample in traveling to the audience. And so in this sample, we have two triangular terminal bases and 3 diagonal struts, and the two terminal bases can be made of a solid member or can be made of cables themselves. And so the kinematics of this system is described by 3 kinematic variables in the general case, which are the length of the cables forming the end triangles, L, the height of the prism, and the twisting angle, the relative twisting angle between the terminal bases. These are 3 independent kinematic variables, while the length of the struts, and B, and the length of the cables, S, is related through compatibility equations to such variables. And regarding equilibrium, one can write, in the general case of symmetric loading, compression loading, one can write the equilibrium equation of one node and can solve these 3 equilibrium equations in terms of the 3 independent variables from the static point of view, which are the force densities in the 3 diagonal cables. We will name in the following these structures a T3 prism. And so we have this force density. As you can see from the analytic expression of these quantities, there is a very strong nonlinear relationship between the forces and the kinematic variables, and the phi, h, and also the forces in the base members are also a function of L. So the additional configurations are shown in this slide, and basically we will examine the compression loading, which starts from this, which is the freestanding configuration. If you manufacture this prism with equal length bars and diagonal cables, it will automatically assume this relative twisting angle, which gives the freestanding configuration. And from this freestanding configuration, you can do a compression loading up to the point in which the 3 bars touch each other. And we will see that this is an important configuration of the system. So what is the fully elastic constitutive response correspond to the model that I have summarized. And in this case, you typically obtain a stiffening response, which is followed by a softening response, and it will end with an unstable snap-through response, and we will be out of consideration in this talk. So this is the typical response: stiffening and softening. But it changes with pre-stress. This is here there is some pre-stress because the system has an internal mechanism. So the fact that we have an initial non-zero stiffness, it means that we are applying a pre-stress to the cables. Otherwise, the initial stiffness would be 0. So we will start with 0 stiffness. This is the case in which the terminal bases are free to deform in their own plane. But we can also model a rigid elastic oscillative response in which the terminal bases here are described with thicker lines, but you can insert, as in the samples that are circulating, some solid members, solid triangles at the end. So in this case, we are keeping the basing rigid, responding rigidly during the compression of the system. So if we don't apply pre-stress, in this case we have a zero initial stiffness, but then the system becomes very stiff and it reaches an infinitely large stiffness in correspondence to the locking configuration in which the bars touch each other. So this is another different response. We can tune with geometry, with the nature of the terminal bases, the response of the terminal bases, but also with pre-stress. For example, by pre-stressing the unit, we will have a non-zero initial stiffness. And now we will also examine another kind of tensegrity units in the talk, which are tensegrity theta equal 1 prisms. Those are obtained by superimposing two T3 prisms, and the two prisms are superimposed, are connected by central cables drawn in green in this slide. So this combination of two prisms, one over the other, is named tensegrity theta 1 because the configuration resembles that of a theta letter of the Greek alphabet. And so this kind of unit are more compliant than the tensegrity prism, especially the ones with rigid terminal bases. And so they exhibit typically a response, a softening response. You can have stiffening and softening depending on the pre-stress that you apply to the cables. We have more variables. The kinematic is more complicated. In this case, we have more kinematic variables, but we can always have a response. In this case, we don't have a dramatic change of the response when we introduce the assumption of rigid terminal base, because the presence of the intermediate cables keep the response compliant, so we don't get this locking response that we have in the case of T3 prism. For this system, also for the one shown before, we run several experimental validations. This is my group, my former group. And so we obtained a confirmation, in absence of pre-stress, we obtained a confirmation of a stiffening and then softening response. This was made by hand. This was a sample made by hand. So now going to the more, this was a long introduction of the topic. Now we'll describe the first of the two metamaterial type responses that we will analyze during this talk. And this first section is related, part 2, is related to the band gap response of tensegrity mass spring chain. This is collaborative work with Luca Placidi, who is here in the audience, and Giulia De Castro Motta, one researcher of my group in Salerno. So we are analyzing two different mass spring systems. One is a diatomic mass spring chain, which shows the two units that I have described earlier. So the T3 prisms and the T theta prisms alternated along the chain and separated by masses. So these masses, two types of masses, we are dealing with a diatomic mass spring chain. These M1 and M2 masses can be different, and so we can play with the band gap response due to the contrast in stiffness of the units. Also, we can also add a constant in mass constant between the lumped masses, so to achieve the band gap response that we need. And this is a simplified model of this chain, in which the springs, the units are described as linear springs, the tensegrity units, because we are linearizing this first section, we are linearizing the response from the reference configuration. Another kind of mass spring chain can be obtained by arranging in parallel T-theta prisms with T3 prisms, standard T3 prisms. So in this way, by designing this system, you obtain an internal resonating system, because this T3 units will resonate, internally resonate during the propagation of mechanical waves, and will introduce a supplementary source of band gap response. The units that we have examined are on the centimeter scale, so the height is of the order of 1 centimeter or 1/2 of a centimeter. And so we have, you can see these are the the properties of the T3 prisms, geometry properties. These are the properties of T-theta prisms that we are employing. And as you can see, the height of the T-theta prisms is doubled as compared to the height of the T3 prisms. This allows the possibility to place in parallel two T3 prisms with one T-theta prism. And you can see that the stiffness properties, which will be used for the stiffness contrast, is due to the different nature of the two prisms, but also from the presence of a different pre-stress. This is the strain, pre-stress strain of the diagonal cables. So by changing this pre-stress, you obtain a stiffness contrast, a supplementary source of stiffness contrast between the units. So for linearizing the response of the system, we recently, working with Luca Placidi, we introduced explicitly the coupling between the twisting angle and the longitudinal displacement. So you can linearize the kinematics, and so you obtain a linear relationship that relates the twisting angle to the longitudinal displacement in this linearized response. So by imposing vanishing boundary conditions at the end of the chain, we end up with this linear relations. E1 and E2 are the two, the apertures 1 and 2 mark the unit 1, which is the T3 prism, the unit 2, which is in the diatomic chain, is the tensegrity theta prism. So we obtain this kinematic relation, and so we can express the kinetic energy of the chain in terms of equivalent masses, which are obtained by multiplying for an amplification factor the physical masses through the torsional stiffness of the torsional stiffness, the torsional inertia of the lumped masses, and the square of this coupling factor. So we obtain equivalent masses that account for the coupling of twisting and longitudinal motion. The overall expression, the kinetic, internal, and external energies are given in this slide, and we can also have some effective external forces which are combined, the axial forces with the twisting moment due to the coupling between the two responses. We end up with an action functional that we can through the assumption of an action principle, we can derive the equations of motion of the system. And finally, by introducing waveforms of the Bloch 2K form, we end up with a dispersion relation relating the time frequency, circular frequency of the propagating waves to the spatial frequency or the wave number, K, through this kind of relation. We have two branches, and the acoustic branches, as in each diatomic chain. But in our case, we can have the two band gap regions, one comprised between the two branches and one above the optical branch. And in these two regions, we can tune these two regions, also playing with the stiffness contrast, which is induced also by pre-stressing the units in different ways, and also through a mass constant. So we can design the material to exhibit the band gap range that is needed for technical applications. And we can develop a similar theory for the Maxwell chain, the one that arranges in parallel theta prisms and T3 prisms. Also in this case, we have a dispersion relation with an optical and acoustic branch, similarly. But in this case, we open frequency band gaps in the response in the dispersion relation, which are tunable, also in absence of mass spring contrast. We don't necessarily need mass and spring constants because of the internal resonance response of the T3 prism. So we have an additional tunable feature of the response. And in addition to that, we can also compare the dispersion relations of a chain with the cap, which accounts for the coupling of twisting and the longitudinal displacement, and a chain that uncouples those responses. Because you can, assuming that the tensegrity units are free to slide against the lumped masses, so that the twisting motion of the units is not transferred to the masses. In this case, you have an uncoupled system, and by passing from this response to this other response, you see that the frequency, the band gap frequencies dramatically change. So we have a highly tunable band gap response. And this is this first part of the talk, examining this linear band gap response. The linear metamaterial response related to the band gap behavior of mass spring chains. Now, I go through the analysis of a different kind of metamaterial response, which is peculiar of this area of metamaterials, the solitary wave dynamics of tensegrity mass spring chain. We always have a chain of units and lumped masses, but now we don't restrict ourselves to the linear response. We analyze the fully nonlinear response. And related to this nonlinear response, we will discover the presence of the support of solitary wave dynamics. So in order to model analytically the response, we propose the tensegrity-like approach, tensegrity-like models, because as you can have seen in the first slides, the force displacement response of tensegrity prism is strongly nonlinear. There are irrational functions, there are trigonometric functions, so it's strongly nonlinear. So in order to end up with analytic results, we introduced some more analytically manageable potentials that capture the main features of the tensegrity response, nonlinear tensegrity response. So the response that we want to model is that of the locking type prisms, the prisms with rigid bases, the standard T3 prisms with rigid terminal bases, as the ones that have circulated, they are now on my desk, which have the terminal bases that are rigid, and then, this is the real stiffness unit. So we first modeled these units. The tensegrity potential exhibit a locking response, which is achieved when the bars touch each other, and in this configuration. So we proposed an analytic tensegrity-like potential, which is given by the red curve, which captures the main features, so the zero stiffness for in absence of pre-stress, and locking type response for U-lock, for U equal to U-lock. And by a change of variables, we pass from this potential that captures the main features of the real tensegrity potential to, we express this potential in terms of a string variable C given by U, the displacement, longitudinal, divided by the initial height of the prism. So by renormalization of the potential, we can write it in the present form. Another response that we will examine is that of the prisms with deformable bases. In this case, we don't have a locking response, but we can have a response that can be either stiffening or softening. In this case, so we have for the fully elastic, the prisms with deformable bases, we can propose this tensegrity-like potential that describes, with a given choice of the constitutive parameters, is able to describe either a stiffening type response or a softening type response. In the softening case, for the reasons that I will show later, we are applying this model to the incremental response from a pre-compressed state, because we want to analyze this, the rarefaction wave solitary dynamics of the softening units. So in this case, this is the force displacement response. It goes also to negative values, because this is imposed from the pre-compressed configuration. So negative F, it means a release of the initial pre-compression. Also in this case, it's the same potential with the different of before for the stiffening case, but with different choice of the parameters. We express the potential in terms of the strain variable, C, as before. And for all the possible choices of this tensegrity-like potential, we have the equation of motion of the generic mass can be written in this standard form. And by introducing a quasi-continuum approach, we transform this equation into a continuum equation given here, where gamma is an approximation constant. So this is a function which has time derivatives and spatial derivatives up to the fourth order. And now we study in this continuum setting, in order to get analytic results, the propagation of a waveform with this expression. C is the strain variable. It's a function phi of x minus by vt, where v is the speed of the traveling pulse. By introducing this waveform in the equation of motion derived through the quasi-continuum approach, we end up with this wave equation that we further manipulate through an integration, a double integration using the asymptotic boundary conditions, to another manipulation. We end up with writing the wave equation of the system in this form. So where phi, with capital Phi, is gamma, the approximation constant, phi is the waveform, prime is the derivative with respect to zeta given by the spatial coordinate x minus vt. So this is this function is related to the phi squared and v tilde, which is the normalized potential. So we will study this function f in order to prove the existence of solitary waves, and also the speed ranges that support the propagation of solitary waves. Let's study, through a Weierstrass approach, we study this function phi. So phi, f is gamma phi squared. So we can see that due to this, we study the positivity of phi and the null point, the 0 points of f. So the double 0 points of f give asymptotic point of the traveling pulse. So if we show that f has two 0 points, two double 0 points, we can prove the existence of two asymptotic points. If we, in addition, we prove the existence of a 0 point of order 1, we obtain an inversion point of the wave. So since we were able to show that our f that derives from the assumption of the interaction potential that replicates the real tensegrity response and the adoption of a quasi-continuum approach, the f of the three cases that we will analyze, all those three cases have the f that shows two double 0 points and one single 0 point. So let's start with the locking type prism. In this case, f has this expression. As you can see, the 0 points of phi, which is the shape, the pulse, the 0 points of phi are 2 points of order 2 for f equal to 0, are the asymptotic point of the traveling wave. And the 0 point of these other terms in brackets gives the inversion point. So phi equal to phi star which makes this quantity 0, is basically gives the peak of the pulse. So we obtain the peak value of the pulse by setting this quantity to 0. Then, in order to have f greater than 0, we have some restriction on the wave speed also. So we have a minimum value that ensures the positivity of f. F must be positive because it's defined as gamma p prime squared. So the minimum value corresponds to the speed of sound in the linearized system, but we have also a maximum value of v, which this is the maximum wave speed that is supported by the system. So the wave speed is not constant, the response is nonlinear, and we have a maximum speed. When the wave reaches this maximum speed, the system gets into a rigid state because all the units are compressed at the locking configuration. So the system becomes rigid. This is the maximum speed supporting the propagation of these pulses. And we have also obtained analytically the shape of the pulse through this equation. By solving this equation, we obtain p as a function of z, and inverting, we obtain by inverting this relationship, we could plot the shape of the solitary waves that exist due to our previous analysis, and also the maximum value of the strain that is traveling can be achieved at the peak of the pulse. So as v tends to the maximum value, maximum possible value, the solitary waves have a peak-on kind of shape, which confirms previous numerical results that we obtained through numerical simulation using the real tensegrity potential. And so we had a good matching between our analytical predictions based on the tensegrity-like potential and the numerical solutions obtained through the real tensegrity potential, which indeed exhibit a monatomic wave of monatomic shape of the traveling pulses in the high energy limit. In the high energy limit, the traveling waves are concentrated on one single unit at a time. One single unit at a time is stressed by the wave. This is the case of the locking type response. Now we can also describe the other two models, the models with the deformable basis and the stiffening and the softening case. For the stiffening case, we have similar results. So we also have, we prove the existence of solitary waves with two asymptotic points and one inversion point. And similarly, we obtain again two extreme values, two bounds for the speed of the traveling wave. And we again obtain a pulse, which is a bell-shaped pulse. It's less, we don't have the we don't observe the peak-on nature of the pulse as in the previous case, but still we have the propagation of compression pulses, which variable speed and variable maximum peak value, depending on the speed of the traveling wave. The final case that we examine is that interesting for our technical applications of these behaviors, which is the rarefaction wave response. So in the case of the softening response, we, instead of having a positive value of the pulse, of the wave profile, we have a negative value. So basically we are able to reduce the initial compression of the system. So we let the pulse, the minimum value of the pulse be 0 because we didn't want that the system enter a loose state. So we examine the region in which we are able to reduce the initial pre-compression of the system, generating a rarefaction wave, as I have showed in the first slides. So also in this case, we run a numerical comparisons with the literature results. So we were able to validate our tensegrity-like approach against numerical results with the made use of the real tensegrity potential. So now, finally, the final part of the talk will be about this, the solitary wave dynamics of 2D and 3D lattices. Because so far we have analyzed only 1D systems. We wanted to go to analyze other more complex systems. And so we studied 2D and 3D systems, which consists of strips of units or more than one single unit over the thickness of the system, or also plates made by tessellating tensegrity units. And so we discovered some interesting results. In this case, we had only numerical simulations. We plan to develop analytic approaches in the future, possibly. The systems that can be studied are different. You can have a variety of geometries. And where is the source? In this case, obviously we don't have prisms. In this case, we are analyzing different kinds of units. Where does the nonlinearity come from? So in the system, in the 2D and 3D system, since we are not analyzing prisms but other arrangements of the nonlinearity comes from the interpenetration, the penetration of adjacent units one over the other. So the cables get into exhibit nonlinear stiffening response due to the penetration of the fact that the units are not perfectly aligned. So we have this, in this system, we have a penetration of one unit over the other, and this is both in the 2D case and the 3D case. We also have this penetration effects that generates a stiffening response. So these behaviors, what kind of, these are the units that we analyzed. They assume the adoption of 3D printed units made of this titanium alloy that we have employed for these samples, and some lead masses that can be added at the tips of the bars and also at the interfaces between the units. So this is the 2D illustration of the kinematics of one 2D chain. What are the responses that we observe in this case? We observe some peculiar response in which I will first run this movie. This is a strip made of 3 units over the thickness. Okay. Okay. So here in this case, you see that the system supports the enucleation of a compact compression wave. This is a stiffness behavior that we are analyzing, but in on the back, at the back of the leading compression pulse, which is confined in a limited number of units and is reflected at the wall, we have a thermalization zone. So in this 2D and 3D system, we observe a thermalization zone behind the point of application of the impact, which is accompanies the formation, the nucleation of a traveling compression pulse. And so we observe this response in different systems. This is a 3 by 50 strip, 3 units in the transverse direction. We also studied numerically in order to, since we don't have analytic results here, in order to prove the solitary wave nature of the pulses, we studied the collision of 2 pulses traveling in opposite directions, because if you have a real solitary wave, the solitary wave should emerge unchanged, unmodified after the collision. And indeed, we observed that the 2 pulses continuously traveling after collision with nearly unmodified speed. So this confirmed, from the numerical point of view, the solitary wave nature of these pulses. And we repeated the simulations for different geometries by adding units in the transverse direction. And so what we observe is that by making the strip more thick, we have obviously more the pulse is the width of the pulse is thicker in the transverse direction, but it gets more reduced. More reduced in the shrinks in the longitudinal direction. So we have here we have only packets of 2 units that are that carry the solitary pulse, while in the strip, more thin strip, we have more units, 4 or 5 units that carry the solitary pulse. And I want to go to we also had experiments to in a plate. And also in this case, we observed the deviation of the pulse due to the chiral nature of the lattices that we have shown. And we have had, I want to go faster because we need to go to the conclusions. We observed this behavior also in 3D beams. So this is a 3D arrangement of tensegrity. So also in this case, we have a thermalization zone which is on the back of a leading compression pulse. So going through also in the case, we studied the collision effect. What is the use of these responses? The possible use is that of designing an acoustic lens that is able to impact with this compact compression wave if we arrange in parallel more strips and we give some delays, we apply some delays in the impact loading of the different units, we can generate in an optimized wave, compression waves that can travel fitted distances in a house medium and can focus at a given focal point. It can be designed accurately. This focal point could be, for example, a tumor mass or a defect to destroy in a material. So, going to the conclusions, we have observed these final part simulations to do a 3D systems that highlight the propagation of compact compression pulses in front of thermalization zones, and this compact compression waves travel on localized packets of unit cells, and they exhibit energy leaking, limited energy leaking. So this is an important result because so far we have not modeled energy dissipation. So there is the leaking energy, which the leaking energy we are referring to is just the transfer of energy from one unit to another unit in the system. And so what are the possible technical uses of the behaviors that we have observed? We can use bandgap materials as waveguides, vibration isolation pads with a tunable response. The compressive solitary wave dynamics can be used for designing devices that can focus mechanical waves in a host medium. And the softening type solitary wave dynamics can be used to design radically new impact protection systems that don't necessarily require energy dissipation, but just the transformation of an impact disturbance into rarefaction wave to a softening type geometric nonlinearity. And so the future directions are that we want to pursue in future work is a multi-scale modeling of the behaviors that we have studied, the study of the stability of the solitary waves, dynamical tests. This is a challenging point because we need to build systems with a large number of units, and also the fabrication testing of vibration of engineering applications of the systems that I have briefly discussed. So I wish to thank you very much for your attention and supplementary materials.